Alrighty. So today we'll be talking about section 5.2, which is all about the binomial distribution. So I learned something distressing as I was preparing today, which is that my calculator app does not actually have any of the distribution stuff on it. So what I'll be doing is showing you where you could find it on your calculator, and writing out the commands to get. And then when we actually start to do some problems, I'll write out what we would need to plug into the calculator, and won't necessarily write down the numbers that we get, since the calculator app that I have won't tell me those numbers. So we'll do what we can with that, and I will see if I can't find a better solution moving forward. But for binomial distribution, this is a discrete random variable, right? So it's going to be capital X, right? And it's going to be binomial, and it's always going to have an N and a P associated with it. So how this works is something is binomial if the associated experiment has n trials. Right. The second thing that needs to be true is the trials need to be independent. Third, each trial has the same two outcomes, and the one we are counting is called a success. Right? Now, we may be counting how many times does a particular piece of machinery fail when it does its job 50 times, right? But we still call, in that case, the probability that it fails is its probability of success. It's really weird, but whatever the thing we're counting, that's what we call a success, and P is the probability of getting a success on a trial. Right? So this is going to count successes. Right? And again, it counts something. It counts one of these two outcomes, and whichever one is the one we're counting is the one that gives us P, and so it's the one that counts as being a success, right? And so if you know it's going to be binomial, you don't have to do all that multiplying and adding up to find the expected value for binomial. It's just going to be n times P. Variance is just n times P times 1 minus P. And we don't need a table because we have a formula. The probability that x equals a particular value is n choose x, p to the x, 1 minus p to the x. So a brief digression. We didn't need all the stuff that came from the section that choose comes from, but we did need some of it. So n choose x is shorthand for n factorial divided by x factorial times n minus x factorial. And n factorial is shorthand for n times n minus 1 times n minus 2 all the way down to 1. Right? So for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Right? So for the most part, that stuff you'll be plugging into your calculator. Right? And specifically, the way we want to do this is if we want to find the probability that x is equal to x on our calculator, let me show you and then I'll come over here and write it to keep it down for prosperity. You're going to go, so this variables button, that's not actually where we want to go. We want to go to the distributions button that is beneath it. So we hit second and hit the variables button, and that takes us to distributions, unless I hit it too long. It's probably really hard to see because it's grayed out because I can't do it. But if we come down here to this guy, to column A here, it says binom PDF. Right, and the one beneath it is binom CDF. So the binom is binomial. The PDF is the probability distribution function. So that's the first one we'll be talking about. CDF is the cumulative distribution function. So that's where you find it on your calculator. Okay. Sorry for the jump. I'm going to cut out the portion where you get to see the all of my files, largely because I don't want them going up on YouTube. So hopefully it's not too jarring. But the probability that big X equals little x is binom CDF. Oops. Binom PDF for this one, because we want a probability. NPX. Right, so N and P come from the distribution itself. Right, these come from the capital X, and this little x is whatever shows up over here. Right, now to use the calculator to answer more complicated problems, right, so if we wanted to do this by hand, we would have to figure out the probability that x equals 0, plus the probability that x equals 1, plus, and we'd have to keep doing that until we got the probability that x equals x. And I don't know about you, but that sounds horrible. And what's much more useful is to have our calculators figure out binomial CDF, right? That C, as I mentioned before, is cumulative. So it adds up all the probabilities that are accumulating up until you get to x. And there you want to put in NPX again. And then if you want to do probability that x is greater than or equal to some x, right? Again, if you do it by hand, this is going to be the probability that x equals x plus the probability that x equals x plus 1, right? Because we're counting, we can't actually get to the fractional values. The probability that x equals x plus 2. And then we got to keep going until we get the probability that x equals n. Right? Again, that doesn't sound like a whole lot of fun. Right? But this CDF is always for less than statements. So what we have to realize is that we can use the complement rule that we talked about last chapter. Right? So the opposite of being greater than or equal to x is being strictly less than x. Right? So those are your two options. You can either be greater than or equal to, or you can be strictly less than. Right? Now this again is not quite what we do with our binomial CDF, but since we're only doing counting numbers here, you can say that that's less than or equal to x minus 1. All right. So then we would plug this into our calculator. 1 minus binom CDF of n p x minus 1. Right? Whatever that winds up being. Right? So that's what I strongly recommend for finding these probabilities, even though I won't be able to actually type it out myself and have the calculator give us an answer. I can at least show you what you need to plug in. Right? So let's do some problems. So are the following random variables binomial? Right. So A, draw a card, record the suit, and replace. Uh, 10 times. Second one, oops, let me give myself some space. Second one, draw a card, record whether it's red or black until the deck is empty. Right. C is going to be the number of free throws made per game. And lastly, D is going to be the number of free throws made out of the last 20. Now let's say the next 20 so it can be appropriately predictive. Right? So the first one is not a binomial distribution because there are 4 outcomes. Right? So it's a repeated trial. Drawing a card counts as a trial. So drawing a card is a repeated trial, and it's repeated n times, so that's fine. But each of those trials, when you draw the card, could be one of 4 different things. Right? There are 4 different suits, so there are 4 different outcomes for each individual trial. This replacing here does indicate that the trials are independent. So really the only rule being broken is that there are 4 outcomes. Right? This next one is also not a binomial. Because while there are 2 outcomes, right, we fixed that part. We've restricted ourselves to red and black. There's a repeated experiment. We're drawing a card, and we're doing it a specific number of times. We're doing it 52 times. But the fact that we're not replacing the cards means that the trials are not independent, right? Whatever card, if you drew a red card first, that means the second card is less likely to be red than if you drew a black card first, right? So what you've already drawn changes the probabilities for all the draws that come after it. So in this case, the trials are not independent. All of the other rules are fine, but the trials are not independent, right? So this third one is also not binomial because there's actually an infinite number of outcomes. Right? Because you could get no free throws in any given game. You could get 1, you could get 2, 3, 4, 5, 6, 7. This gets increasingly unlikely, but technically there's no reason any of those outcomes are impossible. We don't specify how many trials are being made here, so that's another problem with it. That's an easier one to fix, right? You could just say for the next 10 games. And fix that, right? Because playing a game is the trial in this case, right? But the outcome of the trial, which is the number of free throws, there's an infinite number of possibilities there. For the last one, this is a binomial, right? So the trial is making a free throw. We're going to do it 20 times. And the outcomes are, or I guess this shouldn't be making, this should be shooting. I suppose I've never been quite sure of the right verbs. So the outcome is making the shot, or scoring? I don't know. I wish we were in a classroom because somebody there could inevitably tell me what the appropriate verb for it is. But the two outcomes for any individual free throw is whether you score or you don't score, right? The problem with C here was that the trial being each game meant that there could be multiple free throws per game, right? Here, with the trial being a throw, a single throw, that's either going to make it or not. The counting part of it comes from the definition of binomial, right? Binomial counts something. So the counting part of it here comes from the definition of binomial, whereas here, instead of counting a particular outcome, we're counting something within each trial. So we're getting more than two outcomes. Right. So the tricky thing here, so this could be tricky with independent, right? Technically, we don't have enough information to say that, right? It's quite possible that the free throw shooter is someone who chokes, and so if they miss their first shot, they're more likely to miss the next one, right? There's some psychology to it. But it's also not guaranteed to not be independent. And a lot of times when there's not a particular reason to know that it's not independent, we'll take that as an assumption so that we can actually work the problem this way. Right? So we're actually going to use that distribution and say have a word problem to do with it. So a particular player has an 80% free throw percentage, and I'm hoping that my understanding of that particular stat is correct, that means that they make 80% of their free throws. Out of their next 20 free throws, what is the probability that they make exactly 10 of them, more than 15 of them, less than 7 of them. Right? So again, here comes the point where I really want to be able to plug it into my calculator, but the one I can show you and the one I have on hand won't let me do it. So instead, I'm going to answer these questions with what you would plug into your calculator. Right? So, given my understanding of this stat is correct, and this means that whenever this player makes a free throw, they score 80% of the time, then our probability of success is going to be 80%. N is going to be 20, because remember, a trial is shooting a free throw, and we're talking about their next 20 free throws. So the first question is saying, what's the probability that x equals 10. Right, now we could do this as a formula. We would have 20 choose 10 times 0.8 to the 10 times 0.2. Let me do it step by step. 1 minus 0.8 to the 20 minus 10. So that would be 20 choose 10, 0.8 to the 10, 0.2 to the 10. Right, and we could plug that into our calculator and get a number. We could also say that we wanted the binomial probability distribution function where n equals 20, p equals 0.8, and x equals 10. Right, so either one of those, if we plugged it into our calculator, we should be able to get an answer for it. We'll go on an adventure real quick and check on something else. Maybe it's under math. There we go. So n choose r, that guy there, right? If we wanted to do 20 choose 10, then we want 0.8 to the 10. And then we want 0.2 to the 10. There we go. So we could do it that way, and we get that there's not a very good likelihood, right? That's 0.2%, that they make exactly 10, right? And that's probably because they're more likely to make more than that, right? With an 80% free throw shot. So this one I can do just fine on my calculator. So, all right, we went to our calculator, we plugged this in, we got 0.002. Right? The other question, the probability that x is greater than 15, right? This is the type of thing that it's really good to use the CDF for, the binomial CDF. But we can only do that if it's a less than statement. So we need to notice that this is 1 minus the probability that x is strictly less than 14. Right? So this would be 1 minus binom CDF, same n, same p, and, oops, that shouldn't be 14, that should be 15. Right? Because if you're not strictly greater than 15, you're less than or equal to 15. Right? The minus 1, that'll come later. Right? So we would plug that in and have our calculator go. To do it the other way, I really don't recommend. It requires inputting like 6 things into your calculator, hoping that you got all the parentheses right, and that there were no typos. I strongly would recommend using your calculator to get a binomial CDF. So the other problem is we want to know what's the probability that x is less than 7. Now this one is less than, and that's the type of thing binomial CDF talks about, but binomial CDF is specifically less than or equal to. So we need to recognize that if x is a counting number and x is strictly less than 7, then x is less than or equal to 6, right? Because that's the next counting number down. So this is binomial CDF, same n, same p, different x. Right? And again, we plug that into our calculator and it gives us something as an answer. Right? All right, so that's the binomial distribution. We have one more discrete random variable to talk about, and then we will hop into some continuous random variables next up. All right. Alrighty.